Hello everyone, I am Salwa Kobeissi and I'm going to present to you today our paper entitled Rec2Poly Converting Recursions to Polyhedral Optimized Loops Using an Inspector-Executor Strategy. This paper is written with Alain, Ketterlin and Philippe. We are members of the Camus team at INRIA and we are based in Strasbourg at the iCube laboratory, also as parts of the CNRS and the University of Strasbourg. First of all, I'm going to introduce to you our work domain, motivation, inspiration, challenges, and objectives. Second, I'm going to present our proposed solution, the Rec2Poly framework. Third, I'm going to show you some experiments with their results. Fourth, I'm going to mention some related works. And finally, I'm going to sum it all up with a conclusion and perspectives. Here we begin. There may be a huge gap between the statements outlined by a programmer in a program source code and the instructions that are actually performed by a given processor architecture. This gap is due to the way the compiler and the final processor hardware interpret, translate, and transform these instructions. In advanced modern compilers, not only is there a possibility to apply optimizations statically at compile time, but also there is an opportunity to apply efficient optimizations as soon as the actual runtime behavior is discovered. Such optimizations are dedicated to specific control structures and memory access patterns. Loops, particularly affine loops, are among these structures that constitute a huge computation part of a program execution and benefit from advanced and sophisticated optimizations mainly based on the polyhedral model. Among time-expensive structures beside loops, we also have recursions. However, unlike loops, recursions do not benefit from very advanced optimizations. Their optimizations are mainly based on task parallelization. It's well known that a recursion can be rewritten as a loop, usually as a while loop in addition to a data structure replacing the call stack. Traditional compilers tend to optimize recursive codes by eliminating recursions, specifically tail recursions, where the recursive call is the last instruction in the function. Recursion to loop transformation optimizes the program by reducing the overhead induced by accessing the call stack with every recursive invocation. In general, static recursion to iteration conversion may not allow applying further advanced optimizations because the final equivalent loops may have complex bodies with too many if branches. So, in this study, we are interested in optimizing exclusively recursive codes whose behavior can be rewritten as polyhedral loops and that eventually can benefit from polyhedral optimizations. Now, I would like to present two concepts and terms used in our work. First, the polyhedral model. The polyhedral model is a mathematical framework that is used to model programs, particularly affine loop nests, as an abstract representation. It provides accurate data dependence and memory pattern analysis, in addition to automatic optimizing and parallelizing transformations such as loop tiling, skewing, and interchange. Second, the Inspector-Executor paradigm. This is a well-known concept in code compilation. It guides code transformation and optimization of irregular computations by collecting information that is only known and accessible at runtime, such as memory access patterns. It's composed of the inspector, which is a light version of the code that collects runtime information, and executor, which is an optimized version of the code that uses this collected information. This study has been inspired by Apollo, which is a speculative polyhedral compiler and loop optimizer implemented by our team. Apollo is capable of applying polyhedral transformations on loops that are non-optimizable by classical polyhedral optimizers. Classical polyhedral optimizers such as Pluto and Poly are only capable of optimizing loops whose structure is affine at compile time. On the other hand, Apollo can detect loops whose runtime behavior is polyhedral compliant, even if they are statically non-affine. To the right, we have a figure showing an example of an affine runtime behavior of memory accesses of statically non-affine loop. Apollo detects such behavior and applies polyhedral optimizing transformations to the corresponding loops at runtime. Also, it verifies these transformations using the Inspector-Executor paradigm. In our work, we are interested to extend the Apollo approach and apply it on recursive codes. The challenge faced to extend this approach beyond Apollo is that Apollo transforms loops into equivalent polyhedral compliant loops, so we don't have a change in structure. This requires analysis and verification only for memory behavior. On the other hand, we transform recursions into equivalent polyhedral compliant loops. That is, we are transforming a structure into a totally different structure. For that, not only must we analyze and verify the memory behavior, but also the control behavior. Our objective in this article has been to implement Rec2Poly, which is a Clang LLVM-based recursion optimizer aiming at, first, optimizing recursive codes through reliable and efficient transformation into equivalent sequences of affine loop nests. Second, optimizing the latter using the polyhedral model, that is, extending the scope of the polyhedral model to optimize recursions. The originality of Rec2Poly is twofold. One, that it seeks a polyhedral compliant runtime behavior in recursions, and two, that it uses an inspector-executor scheme, not only verifying memory access patterns, but also the control pattern. Now, I'm going to present and explain the solution proposed in this paper, which is the Rec2Poly framework. This schema sums up the phases of the framework. At the beginning, given a recursive code, Rec2Poly performs code analysis. The analysis information obtained is then used in all of the next steps. Then, Rec2Poly performs variable globalization and instrumentation to get the program control and memory behavior trace that is fed to the nested loop recognition algorithm that models this trace as an affine loop model if possible. Afterwards, Rec2Poly generates the inspector code in addition to the optimized affine loops that constitute together the final code. Now I'm going to explain in details each of these phases. First phase is the code analysis phase. It takes as an input the recursive code and gives as an output the analysis information. In this phase, Rec2Poly performs recursion detection. Using the call graph of a program, it searches for strongly connected components. A strongly connected component means that there is a recursion among the functions represented by the involved nodes. Here in this arbitrary call graph example, we have function C in a direct recursion with itself, and functions C and E in an indirect recursion with each other. Then, Rec2Poly performs recursion reachability recognition. By reachability, we mean the set of functions reachable or invoked directly or indirectly by a recursive function. In this example, functions D, F, G, and H are recognized as reachability functions. In addition, Rec2Poly executes recursion source recognition, and by source we mean the set of functions participating in a sequence of calls starting from within the body of the outermost loop in the code to a recursive function. We are interested in analyzing such functions because, in addition to recursions that exhibit an affine behavior, we are also interested in recursions that distort affine loop nests already existing in the code. In this example, since function C, which is a recursion or a recursive function, is called by B, that is called by A from within a loop, Rec2Poly includes A and B as source functions. Then, Rec2Poly collects impacting basic blocks. This is achieved by, first, getting memory writing instructions, second, collecting all computations leading to a memory access, which are called the backward static slice, third, obtaining the parenting basic blocks. Finally, in this phase, Rec2Poly performs intra and inter-function memory behavior analysis. Why is that? Because in different executions, data structures may be allocated at different memory addresses, yet the memory behavior may stay the same relatively to the base addresses of the data structures. So we associate an accessed memory address to its base address for global data structures and local data structures. For global data structures, accessed addresses can be directly associated to their base addresses. On the other hand, as for local data structures, Rec2Poly needs to perform intra-function analysis to associate the access addresses to the base addresses visible in the scope of the parenting function where parameters are the furthest analysis point. Also, in case the accessed data structure is a function parameter, Rec2Poly performs inter-function analysis. In other words, the analysis propagates outside the function to trace arguments fed to the function to finally associate the address access to its actual base address. The second phase of Rec2Poly is variable globalization and instrumentation. It takes as an input the recursive code in addition to the analysis information obtained by the code analysis phase and gives as an output the instrumented recursive code. In this phase, Rec2Poly globalizes local variables and adds function invocation counter. This is because local data structures are allocated on the call stack at every impacting function invocation. So accessees do not exhibit an affine behavior across all invocations, and they must still be referenced when loops replace the functions. This helps handling data dependencies among instructions among different invocations. Then Rec2Poly adds printing statements to produce the trace, which is to instrument every impacting basic block ID and the relative offset of the touched memory address for each memory instruction in the current basic block. The relative address is computed by subtracting the base address from the actual address accessed. After the instrumented recursive code is generated, it's then run to get the trace of the control and memory behavior of the recursive code. Then Rec2Poly starts its third phase, which is nested loop recognition, that takes as an input the trace and gives as an output an affine loop model of the trace in case possible. In this phase, Rec2Poly uses a nested loop recognition algorithm whose applications are 1. Program behavior modeling for any measured quantity such as memory accesses, 2. Execution trace compressing, and 3. Value prediction. Besides using NLR to model memory accesses, which is NLR's original goal, Rec2Poly uses it to model sequences of basic blocks IDs, that is the control. If NLR builds affine loop nests including the interesting basic blocks IDs and memory addresses interpolated by the constructed loop indices, then the generation of equivalent affine loops may be performed later on. Moreover, Rec2Poly uses a more advanced version of NLR that detects that the affine modeling of a trace may be based on specific or unknown values. So it discovers these values and exhibits a memory behavior which is actually not fully affine, where some coefficients in the affine functions may be lists of values instead of constants. To the left we have an example of an NLR model for a linear control and a linear memory behavior. We can see that the coefficients are constant. In comparison, to the right, we have an example of an NLR model for a linear control but a nonlinear memory behavior. In this model example, we have the coefficients as lists of values, each of size 100. And in the first list we have, for I0 equals 0, the first coefficient value is 3. For I0 equals 1, it's 5, and so on. Then we have the fourth phase of Rec2Poly, which is generation of the inspector. It takes as an input the recursive code, the analysis information, and the affine loop model, and gives as an output the inspector code. Now in this phase, Rec2Poly generates a fast parallel inspector composed of 1. Trace generators. Trace generators are minimal versions of the original recursive program devoted to producing the same kind of execution traces as the one generated at the profiling phase. We have 1 control trace generator and as many memory trace generators as required. 2 verifiers, whose role is to check if the generated traces are still compliant with the NLR affine loop model. And 3. The parameter saver, whose role is to collect function input or parameter values. All of the trace generators, verifiers, and the parameter saver are launched in parallel using pthreads. In some cases, further inspector optimizations can be applied, such as when the same array is accessed several times through indices computed using the same induction variable. Only one access is worth being verified in this case. So we can reduce overhead by removing redundant memory trace generators and verifiers. This is an inspector example corresponding to the arbitrary call graph example shown at the beginning. Thread 0 launches the parameter saver. The other M threads handle the trace generation verification process in pairs in parallel. Each trace verifier pair has N buffers to process on. For example, thread 1 generates the trace and starts by filling the first buffer. When this buffer is full, the verifier in thread 2 is notified by a semaphore and it starts verifying the values of the first buffer. Simultaneously, the trace generators proceed on filling the second buffer and so on. The fifth phase of Rec2Poly is generation of optimized affine loops. It takes as an input the recursive code along with the analysis information and the affine loop model and gives as an output the optimized affine loops. In this phase, the executor or the optimized affine loops are generated. In case of loops with an affine control and an affine memory behavior, Rec2Poly optimizes them using the Pluto Polyhedral optimizer. But since the transformations are applied at the level of the LLVM intermediate representation, Rec2Poly needs to feed Pluto with an open scope representation of the loops that is a format understood by Pluto. In case of loops with an affine control but a nonlinear memory behavior, Rec2Poly cannot apply polyhedral optimizations, but there is still a possibility to apply efficient loop parallelizations after performing a dedicated dependency analysis as follows. First, Rec2Poly builds independent sets of iterations. Second, it breaks the outer loop into two nested loops, where the outer loop iterates over lists of loop indices values, and the inner loop iterates over the indices values inside each list. Finally, the outer loop is parallelized into parallel OpenMP threads. At the end, given the inspector code with the optimized affine loops, the final optimized code is generated. Now, I'm going to show you two experiments using Rec2Poly. The first one is Heat, a recursive C program whose call graph appears in this slide. We can notice that there are two cycles over the node of the function divide, meaning that divide is in a direct recursion due to two self-recursive calls. The reachability of this recursion is composed of the functions comstripe, initGrid, and allCgrid. We are particularly interested in comstripe for it includes interesting affine loops. So the existing recursion actually interrupts their behavior, and getting rid of it may allow applying sophisticated optimizations. Also, divide is invoked from within a loop in function heat, so the source of this recursion is heat. Here we have a part of the NLR model of the control and memory behavior of the recursive heat. It is fully affine, so polyhedral optimizations can be applied to this program. Now it's time for some experimental results. On the horizontal axis, we have the number of iterations of the loop invoking the recursive function divide in function heat, while on the vertical axis, we have the execution time of the program. All the comparisons I'm going to make are with respect to the performance of the original recursive code represented by the red line. For an upper bound of 500,000, the inspector code, which is composed of 10 trace generators and 10 verifiers, and whose performance is represented by the purple line, performs about 29% better. The blue line shows that the optimized inspector code, composed of only 5 generators and 5 verifiers, as half of the redundant memory addresses are ignored in the verification process, executes about 56% faster. Furthermore, the iterative code optimized by Pluto performs about 86% better, which is so powerful. Overall, the optimized executor and the optimized inspector codes together, whose line is orange, run about 24% faster than the original code. The second experiment is performed on the gem matrix multiplication, whose call graph is shown here. In this code, we have an indirect recursion involving these 4 colored functions. Its reachability is function sgemtrans2, which is even much more interesting since it includes sequences of affine loops. The problem in this recursion is that it accesses an array with every invocation, and with every invocation the array is divided into 2 sub-arrays, and then each of them is used as a parameter to a new invocation. So memory behavior should not be linear in this case. Here is a part of the NLR model of the trace of this recursive program. It shows that the program exhibits a linear control but a non-linear memory behavior, as the coefficients values are represented as lists. Here are the experimental results of this program. On the horizontal axis, we have the matrix size, while on the vertical axis, we have the execution time of the program. All the comparisons I'm going to make are with respect to the performance of the original recursive code represented by the red line. For a matrix of size 6400 by 6400, the inspector code, which is composed of 7 trace generators and 7 verifiers, and whose performance is represented by the purple line, performs about 49% better. The blue line shows that the optimized inspector, composed of only 4 generators and 4 verifiers, executes about 55% faster. Then the iterative code optimized by non-polyhedral optimizations by Rec2Poly performs about 87% better, which is also great compared with the Pluto optimizations in the previous experiment. Overall, both of the optimized executor and the optimized inspector codes together, whose line is orange, run about 45% faster than the original. Now I'm going to mention some related works. First, we have Apollo, which was presented earlier as our inspiration, and now as a very quick revision. It's an optimizer dedicated for iterative codes only. Second, we have Polyrec, which is an optimizer committed to particular forms of recursions, such as nested recursive invocations, where data is organized in inner and outer trees. It optimizes them by polyhedral scheduling transformations. Third, there is Adriatin, which is a compiler retrieving directive-based parallelism from recursive functions. It addresses recursive functions whose parameters remain unchanged among recursive calls except for one integer parameter. Finally, there's a way to optimize recursive task parallel programs by listening task creation and termination overhead. In conclusion, in this study we present Rec2Poly, which is the first attempt of speculative recursive program optimization involving the rewriting of the target code. We also show that some recursive programs may take advantage of efficient and powerful optimizations originally dedicated to affine loops only, such as the polyhedral model. As a future work, we would like to investigate strategies to optimize and parallelize more the inspector to lower its time overhead, because the final performance of the final generated code mostly relies on the performance of the inspector. So this way, we can even optimize more the final generated code. At the end, I would like to thank you for your attention, and I would be happy to answer your questions.